to talk about electrochemical cells. Now, we are going to discuss two electrochemical cells, and the first one is called a voltaic cell. And a voltaic cell, it uses spontaneous redox reactions to generate electrical energy. So let's dive into what that actually means. So if it is spontaneous, that means that delta G is going to be less than 0. It is negative. And the system will do work on the surroundings. And this is essentially how batteries work. Now, the other type of cell that we have is an electrolytic cell. And an electrolytic cell uses electrical energy. To drive a non-spontaneous redox reaction. And we are not going to focus on this nearly as much in this class. So what that means is delta G is going to be greater than 0. Delta G is going to be positive, and the surroundings do work on the system. Now, whenever you're looking at these electrochemical cells, they are made by using two electrodes placed in electrolytic solutions. So these cells are made by using two electrodes placed in electrolyte solutions. Now remember, an electrolyte solution is one where you have ions floating around. So it needs to be a soluble ionic compound in that solution. So the two type of electrodes we're going to talk about in this class that make up these cells are anodes, and this is the electrode where oxidation occurs. So what happens is that means we have produced electrons by the oxidation. So it is going to be our negative electrode. Remember, oxidation is loss of electrons, so the process of oxidation is giving off electrons. Electrons are being produced, if you will, since they are being given off. Now, the other type of electrode we're going to talk about is a cathode. And the cathode is the electrode where reduction occurs. So what's going on here is electrons at this electrode. This electrode gains electrons by reduction. And this is going to be the positive electrode. So since the cathode is taking electrons out of the solution or out of the system, it is going to be positive because you're drawing those electrons in. All right, let's look at the construction of a voltaic cell. Now, something you need to be aware of is a voltaic cell is also known as a galvanic cell, and you will hear them used interchangeably. Now, when you have a voltaic cell, it is a spontaneous process, and you have to divide your reaction into halves so that each half reaction has to be in its own cell. What that will look like for us is we will use either microplates or beakers to make our voltaic cells. So one half reaction will go in one beaker, one half reaction will go in the other beaker, or one will go in one of the microplate cells and another one will go in the other microplate cells. Each half cell consists of an electrode in an electrolyte solution. So each half cell consists of an electrode in an electrolyte solution. And then finally, the half cells must be connected by an external circuit. So in order to complete that circuit though, because that's only one connection, we also have to have what is called a salt bridge. And the salt bridge is what completes the circuit. And it does that because it allows ions to flow through both half cells. So the salt bridge is generally made up of a ionic compound that is soluble. So one of the most common that you will see is something like potassium nitrate, and it is soaked in some sort of gel so that it doesn't just fall out of the salt bridge. So let's look at an example of a voltaic cell. So remember, a spontaneous redox reaction makes up a voltaic cell. So we can look at the reaction between zinc and copper 2 to yield zinc ion plus solid copper. So if we look at this reaction, we can break it up into two half reactions, the zinc side and the copper side. So zinc is going to zinc ion, and in order to do that, it will also produce 2 electrons. Now those 2 electrons are going to react with the solid copper or with the copper 2 to make the solid copper. So if we look at this, we can see that zinc is producing electrons. They are being lost. So this is going to be what is oxidized. Zinc is oxidized. The electrons are being gained by the copper 2. So the copper 2 is being reduced. So remember, we can decide what is going to be present at the anode and what is going to be present at the cathode based on what is being produced and what is being oxidized. So the anode is where the oxidation occurs. So in this case, zinc will be the anode, and copper will be the cathode. Now we have a saying which is an ox and a red cat. And all that means is an ox just means anode is oxidation, and red cat just means reduction is at the cathode. So that's kind of a way you can remember which process is happening at which electrode. So when you look at this, the cations are going to move through the salt bridge from the anode solution to the cathode solution, and the anions will move through the salt bridge from the cathode solution to the anode solution. So if I look at my two half reactions, and remember, they are going to be separated either by having two beakers or by having two microplates. And then we have our other reaction happening on the other side. So over here on the zinc side, we have the cations that move through the salt bridge from the anode solution to the cathode solution. So that might look like the zinc 2 plus moving through the salt bridge to the cathode solution. Now, on the other side, we're going to have the anions move through the salt bridge. From the cathode solution to the anode solution. So in this case, it's going to be the counter ion for your cation, and they are going to be moving back in the other direction. Now, this is very important when you are drawing these cells out. You always want to show the anode on the left side and the cathode on the right side. Another way you can think of it is just start with the anode when you draw these out. So we have two different ways to show the notation for a voltaic cell. The first is just the shorthand. And that is where you just show your solid electrode, and there is a barrier between the solid and the ions. And that barrier is just the solid electrode into the electrolyte solution. And then there is a separation of the two reactions. So those double lines just represent that separation. And I kind of think of it as the edge of the two beakers. And then you have your anions from your other cell, the barrier, and then your other electrode. And in this case, it was the zinc was being oxidized, so it is at the anode. The copper was being reduced, so it was at the cathode. Now, something that is important here, this notation is only for a standard cell. And standard cell just means it is a 1 molar solution. So if you don't have a 1 molar solution, then you must indicate the molarity of your solution. And remember, molarity is not going to go with solids. Solids do not have concentration. It's going to go with your aqueous ions. So if my molarity is not 1, then I need to indicate that. Let's say it is 0.4 for the zinc. So after I write my zinc ion, in parentheses, I will give the molarity. And then I'll show the end of one beaker, the start of the other one, and my ions go first for the cathode, followed by the concentration of that. We'll say that is 0.8 molar. So whenever your concentration is not 1, then you need to indicate what the concentration is in parentheses after your ions. Now, the other way that we can show this is in a beaker diagram. And this is where it is more drawn out. So we have our two beakers. And remember, we put the anode first. So I'm going to draw my electrode right here. And my electrode is zinc. So I'm going to label this as such. It is zinc. In solution, I have zinc ions and nitrate. And this is my anode. And since it's my anode, it is negatively charged. Now I'm going to draw my other beaker diagram, or my other beaker. So this is where the cathode will be. So when I draw my anode, or when I draw my cathode, when I draw my electrode, it is going to be copper for this example that we just did. And in solution, we're going to have copper ions and nitrate. Remember, nitrate is just the counter ion. It can be anything that is soluble. This is my cathode here, and it is positively charged. Now, if you recall, these have to be connected by an external circuit, and this is an electron volt reader, if you will. And the flow of electrons is going to be moving from the anode to the cathode. So it's important to show that flow of electrons. Now, finally, to complete the circuit, we have our salt bridge right here, and we can choose potassium nitrate. So when you draw your beaker diagram, you need to show both of your electrodes. Right here we have our anode and our cathode. Our anode is always given first. You need to draw your anodes and cathodes and then label them as well. Finally, you need to put your your anions and cations in the solution. Show your flow of electrons going from the anode to the cathode. Show your external electron voltmeter, and finally your salt bridge.